Today we will discuss about the bioelectrical impedance spectroscopy development, including hardware and some fine tuning, especially the active electrode part. And then also we will discuss about the calibration of the BIS device. So the figure 1 is the block diagram of the BIS device that we are using right now, for the custom made, and we use the function generator, and that will feed up the current pump, and current pump is going to inject the current to the DUT device on the test. So that's going to be a human body, or in this case we use the just registers. And then active electrode, two active electrode is going to get the signal, and then instrumentation amplifier is going to be amplifying the signal, and then that's going to be into the oscilloscope and reference register, and then voltage from the DUT is going to be measured together. And figure 2 is the PCB, which we use the SMD devices for the minimize the noise and then maximize the the efficiency of this BIS device. And then the right hand side of the figure 2 is the prototype of the active electrode. So here are three results. Figure 3 is the frequency versus the phase angle. Phase angle is very sensitive about the frequency and the device on the test. In this case, we use the 9 different resistors values from 100 ohm to the 1000 ohms. And then, as you can see, for the lower register, we got most of that variance over here. And then as it goes to high, it's pretty much good. It's a linear tendency. And then we create the 4 different scenarios without filters, and then with filters with the 20 picofarad and 10 picofarad, and then we just pick up the good linear. We pick up the setup which shows a good linearity. In this case, the filter with the 10 picofarad at the feedback loop, actual electrode is going to be the best, showing the best the result. And then the filter with the 20 picofarad shows the little bit of DC gains, so we just exclude that. And then voltage ratio is between the voltage on the DUT and the reference voltage, and it shows the linear tendency. And then if you see the end of the 1 megahertz over here, and then it will start to distort the signal. So we have to make all these 3 graphs as linear as best as possible. Then we can, of course, we cannot make it all linear, and then we will just do software calibration or interpolation. So through this study, DC power supply is one of the most important factors to determine, show the linearity, and then small, especially for the low frequency, and then clean power is very essential. Tuning the active electrode by applying the low pass filters and then some feedback by placing the resistor and capacitor in the feedback loop is very essential, because the unity active electrode is very unstable, so we have to really kill any unwanted noises. Low pass filter can minimize the DC offset and noises, and later on we're going to just consider some active low pass, high pass, or band pass filter. Shielding is also one of the variables. Shielding in the current injection cable, and the shielding at the active electrode side is going to be really vital roles, and then we have to consider very different scenarios of shielding. And minimizing distortion at the high frequency above 500 kilohertz up to 1 megahertz is the key to make this BIS device happening, and then currently we are working on that. So conclusion, we are trying to minimize the any nonlinear behavior by tuning the hardware, and then rest of them we will just finish this thing with the software.